Hey there, and welcome to this video. Today we will talk about the MLP Mixer, which was introduced in the paper MLP Mixer and All MLP Architecture for Vision. What you see on the screen is the official GitHub repo. However, it seems like it is still work in progress. It lies on a branch called Linen, and I'm not really sure what the status is and what modifications will need to be done before merging to master. For that reason, I decided to use the code that the authors included in the appendix of their paper, which you can see here. Amazingly, it all fits on one page. Just to be clear, it only contains the definition of the forward pass. Things like the training loop and evaluation are of course not included. However, we don't really mind because in this video we'll only study the architecture. To make things more fun, we will rewrite this Flax code from scratch, and I will try to add comments and explanations. Once we are done, we will implement the forward pass in PyTorch. Feel free to check out the description where I provide timestamps for different sections. This way you can just jump to whatever part you find interesting and ignore the rest. Before we start, I just want to state that I'm not affiliated with any of the authors, and I would definitely encourage you to check the original paper since this video might contain misinterpretations and mistakes. Alright, so what is the MLP Mixer? It is an architecture that is purely composed of multi-layer perceptron blocks, which in essence means that it is only composed of linear layers. According to the paper, the MLP Mixer can perform almost as well as convolutional neural networks and vision transformers on the task of image classification. And that in itself is pretty amazing because the MLP Mixer is not using any convolutional or self-attention layers, which are traditionally believed to be necessary for creating good classifiers. Let us now look at the diagram. It describes the forward pass that starts with an input image and ends with a class prediction. Similarly to a vision transformer, we split the image up into small patches and we embed each of them. And now comes the novel part. We take our embedded patches and feed them through multiple so-called mixer layers. Similarly to self-attention, the output of this mixer layer will have exactly the same shape as the input. The forward pass then continues with a global average pooling that is going to average over the patch dimension. Finally, we send this average tensor through the classifier head to get the class predictions. Let us now focus on the upper diagram where we can see what is happening inside of a single mixer layer. The input is a 2D table where the rows represent different patches and the columns represent different channels of the patch embeddings. The idea now is to learn two mappings. One that takes a single row and maps it to a new row of the same shape. And similarly, a second mapping that takes a single column and maps it to a new column of the same shape. These mappings will be represented by two separate multi-layer perceptrons. The process of mapping all rows using the first MLP is called channel mixing, and its goal is to combine features inside of a single patch. Similarly, the process of mapping every single column using our second MLP is called token mixing, and its goal is to accumulate information over different patches. The mixer block performs one token mixing followed by one channel mixing. I guess the code will make this more clear. Alright, before we start, let me give you a very quick introduction to Flax, and I will focus only on the concepts that will be necessary to understand the forward pass. So if you're wondering what the difference is between JAX and Flax, JAX is an auto-differentiation tool, among other things, and Flax is a deep learning package that is built on top of it. Let us now instantiate a dense or a linear layer. So since we only provide the output features when we construct the dense layer, there will be need for shape inference. Note that Flax modules are fundamentally different from Torch ones because they are not stateful. That means that constructing the dense module did not actually trigger any initialization of weights. This initialization needs to be done separately. And I guess this is in line with JAX's philosophy of being functional. To actually initialize our parameters and do shape inference, we first need to generate a random key. So the key is a random state that will guarantee that we can get reproducible results. What is very different compared to Torch is that whenever there is a function that initializes an array randomly, you need to provide a key. All right, so now that we have the key, we can initialize the parameters of our module. We use the method init that takes in a random key and a dummy array. The reason why I call it the dummy array is that what really matters is the shape rather than the values themselves. The shape of the input will be used to automatically do shape inference on all parameters that are inside of our neural network. These parameters are actually returned by this init method, and as you can see, it's a frozen dictionary, which means that you're not supposed to modify it, and also its values are device arrays, and you can think of them as immutable NumPy arrays. And when it comes to the actual contents, we can see that it holds the trainable parameters of the dense layer, which is the kernel and the bias, with the correct shapes. Note that these parameters are not stored inside of the module as some internal state, and therefore not only you will have to keep track of your module, but also of the trainable parameters. To run inference on our module, we use the apply method. We can see that each row is identical because our input was just once. And as expected, the shape of the output is going to be the number of samples times the number of output features. If you're interested, there is this following method, which is nothing else than a merge of the init and the apply method, so you can initialize the model and run inference at the same time. For debugging purposes, you can make the module stateful by using the bind method. The main difference compared to the vanilla module is that it actually internally stores its parameters, which corresponds to the behavior of PyTorch modules. You can access the parameters under the attribute variables. Another benefit of the stateful module is that you can just call it to run inference. With the original module, it doesn't work. However, with the stateful one, it works. The last topic I want to cover is defining custom modules. The most important thing is that Flask modules behave like Python data classes. One implication is that you're supposed to define hyperparameters as class variables. Let me show you a minimal example. We define two hyperparameters AB as class variables, and we also provide their type. We choose to use the goal method to define the forward pass, and we decorate it with this NN compact decorator. This will allow us to define submodules in line. Note that you could also define the submodules explicitly, but I would refer you to the documentation if you want to know more. By the way, this is nothing else than a multi-layer perceptron. We instantiate our amazing module. However, as mentioned before, instantiating this Python object is not going to trigger instantiation of the trainable parameters. Here I use the convenience method init with output, and note that the input features can be anything. In this case, I set it equal to 7. And the reason why input features can be literally anything is that Flask will do shape inference for us. And when we define this amazing module, we never hard-coded any input features ourselves. So in a way, it's more flexible. And as you can see, the parameter dictionary is storing both of the dense layers that we defined inside of our call method. And looking at the kernels and the biases, the shapes were correctly inferred. All right, let us now write the Flask implementation. I'm not going to add any extra annotations or doc strings to this code since I will keep it for the PyTorch implementation. So let's create a script called official. All right, so we will use INOPS to conveniently rearrange dimensions of tensors. Then we import the Linen subpackage of Flask that will be used to define deep learning blocks. And finally, we import checks NumPy that behaves more or less like NumPy. So here we define a simple two-layer multi-layer perceptron. Note that the number of output features of the second dense layer is equal to the number of features of our original input. This means that the inputs of this MLP block are going to have exactly the same shape as the outputs. More specifically, we will be always dealing with three-dimensional arrays. The first dimension is going to be the batch dimension, and the second and the third dimension will be the tokens and the channels of the patch embeddings. Note that the last two dimensions correspond to the diagram that I showed you, and their exact order will depend on whether we're doing channel mixing or token mixing. Let me quickly show you how dense layers behave in Flask when we give them multi-dimensional input. Note that the behavior is exactly the same as in PyTorch, and that is, it is the last dimension that matters. So we instantiate a dense layer by providing the number of output features. We initialize the trainable parameters, and as the dummy array, we provide a one sample array with the number of input features equal to 3. The sample dimension doesn't really matter for the initialization. What matters is the number of input features. So as you can see, Flask did shape inference, and it prepared the kernel and the bias trainable parameters. What I want to show now is that we can actually keep the trainable parameters the way they are and just add dimensions to our input tensor. So here we provide a two-dimensional array. However, we just changed the number of samples compared to the dummy array, and not surprisingly, Flags was able to deal with it. What I want to show is that you can actually create tensors with arbitrary many dimensions, and the inference is going to work as long as the last dimension is going to be equal to the input features. So as you can see, we simply iterate through the initial dimensions, and then the dense layer is applied using the last one. By changing the size of the last dimension, we break things. All right, now we will implement the mixer block, which is the most important part of the MLP mixer. We define two hyperparameters. The first one is the token's MLP dimension, which is related to the token mixing, and the channel's MLP dimension, which is related to the channel's mixing. And they determine the size of the hidden layer inside of our MLP block. If we disregard the patch dimension, the rows are going to be different patches, and the columns are going to be different channels of our embedding. First of all, we apply layer normalization. Here we swap the patch dimension and the channel dimension, and we do it because we are getting ready to do token mixing. And as described, it is the last dimension that matters when it comes to applying the dense or the linear layer. All right, so we perform token mixing, and then we swap back to have the original shape. And we take the resulting tensor and add it to the input as a residual. We again apply the layer norm, and we do channel mixing, and we take the result and add it as a residual, and that's it. And the final class is going to be the MLP mixer and will represent the entire neural network. Here we have all the hyperparameters, most notably the patch size and the number of blocks. So first of all, we use a 2D convolution to create the patch embeddings. We take the resulting tensor and rearrange it such that we only have 3 dimensions. Note that these 3 dimensions represent the patch, the tokens, and the channels, exactly like we saw in the diagram. Here we instantiate multiple mixer blocks, always using the same tokens MLP dimension and channels MLP dimension. As discussed before, the input shape and the output shape of the mixer block is identical. We apply one last layer norm. We apply the global average pooling by averaging over the token dimension. And finally, we apply a dense layer that has the number of output features equal to the number of classes, and it serves as the classifier. All right, and we're done. 50 lines of code. Now I will implement the MLP mixer in PyTorch, and here I will try to provide more details and explanations. We start with the multi-layer perceptron block. All right, so the first parameter will represent the dimension of the input and the output. The actual value will depend on whether we are doing token mixing or channel mixing. MLP-DIM represents the dimension of the hidden layer. Internally, we will instantiate 2 linear layers and 1 activation. So if the MLP-DIM is not provided, we just set it equal to the DIM. And we instantiate 2 linear layers and 1 activation, namely the Gaussian error linear unit. And now we're ready to write the forward pass. So the input tensor can have 2 different shapes. If we are inside of a token mixing, the last dimension is going to be the number of patches. And if we are inside of a channel mixing, the last dimension is going to be the number of channels. As discussed before, the last dimension plays an essential role because it's exactly that dimension that we applied the linear module to. When it comes to the remaining dimensions, we just iterate through them and we reuse the same linear module. The output tensor will have exactly the same shape as the input one, which is very convenient. We apply the first linear layer, and what you see in the comment is the final shape. Note that I'm using the asterisk symbol because I did not want to give a name to this dimension. As discussed before, the dimension that really matters is the last one. We apply the activation and the shape stays unchanged, and that is because activations are always applied element-wise. Finally, we apply the second linear layer and we end up with a tensor that has exactly the same shape as the input one. All right, now we will implement the mixer block. So the first parameter is the number of patches we split up the image into. Hidden dim represents the hidden dimensionality of the patch embeddings. And then as described, we will have one MLP for the token mixing and one MLP for the channel mixing. And each of them needs to have some hidden dimension that is controlled by these two parameters. Internally, we will have two layer norms and the two MLP blocks. So as always, we instantiate the parent class in order for the PyTorch magic to work. Here we instantiate two layer normalizations, and what is important is that we will do this normalization along the patch embeddings hidden dimension. I already explained layer normalization in one of my previous videos, so I will link it in the description if you're interested. Then we instantiate the token MLP block to do token mixing and also the channel MLP block to do the channel mixing. So the input to the forward method is a tensor of the shape number of samples, number of patches, and hidden dimension. Note that if we disregard the first patch dimension for now, number of patches times the hidden dimension is nothing else than the table that we saw in the diagram, where the rows represent different tokens and the columns represent different channels of the token or patch embeddings. And by the way, if you're confused about the terminology, patches and tokens are used interchangeably. By the way, if you look at this shape, then you can right away see that we would be ready for the channel mixing. However, if we just transposed or swap the last two dimensions, we would be ready for the token mixing. Anyway, the resulting tensor has exactly the same shape as the input, which is again really convenient and is very reminiscent of self-attention. First of all, we apply our normalization, and similarly to the linear layer, what really matters is the last dimension. We then swap the last two columns, which will result in the patches being the last dimension. We perform the token mixing using our predefined multi-layer perceptron. And here we undo the swapping that we did, and the channels are again the last dimension. Here we take the result of the token mixing and we add it as a residual to the input. We continue with the second normalization layer. Then we apply the channel mixing and we again add it as a residual. As you can see, this chain of operations led to an output of exactly the same shape as the input. So the forward pass is done, but before we continue, let me talk about one interesting property of the mixer block. The authors point out that one can implement both the channel mixing and the token mixing using convolutions. So one can actually make an argument that the MLP mixer is nothing else than a convolutional neural network. Let us now try to rewrite both the channel and the token mixing using convolutions. All right, so we will start with the channel mixing. All right, so we create a tensor that has 3 dimensions. There are the patch, the channels, and the patches or tokens. Note that this shape is very convenient when applying convolutions in Torch because it always expects you to have the channels dimension as the second dimension. However, in the forward pass that we just wrote, the channels were actually the last dimension because this shape is really convenient when we are applying the linear layer. And now let us instantiate 2 different modules. So this module linear can be thought of as the multi-layer perceptron. And this convolutional module is a 1D convolution where we set kernel size equal to 1. Note that the stride is by default also equal to 1. And in what follows, I will try to show you that they are basically doing the same thing. So they seem to have the same number of trainable parameters. And these parameters are actually contained in the bias and the weight arrays. So as we can see, it's almost matching except for the weight for the module conv, where there's 1 extra dimension at the end. And since these arrays were randomly initialized when we instantiated the modules, we would now want to make sure they are identical. So now we will take our input tensor X and we will run it through both of these modules. In the case of the linear layer, we needed to permute just before running the forward pass, and that is because the linear layer always uses the last dimension of the tensor. However, after the forward pass, we just undo it. We run the forward pass for the conv module, and it seems like they have the same shape. And now let us compare them element-wise. And it seems like they're identical. So to summarize, channel mixing is nothing else than applying a one-dimensional convolution with kernel size equal to 1. Alright, now we would like to implement the token mixing using convolutions. The main idea here is to use the so-called depthwise convolution. It takes the input tensor and it applies filters to each channel separately. Additionally, we would like our filters to span across all the tokens. So we provide the hidden dimension, which is nothing else than the input channels of our tensor. Then kernel size will be equal to all the tokens. And finally, k can be any number representing the output features. So we create two parameters, the weight and the bias, and they are going to be shared across all the input channels. We replicate the bias and the weight across all the input channels. We then run the one-dimensional convolution and note that the groups is equal to the number of hidden dimensions, which will result in a depthwise convolution. To summarize, the same filter is going to be applied to all input channels. All right, let us now define a couple of parameters. And we instantiate this custom convolutional layer that we have just written. And note that the kernel size is equal to the number of patches. And this way we're going to span across all the tokens. We also instantiate a linear layer that more or less represents the multi-layer perceptron that does the token mixing in the original code. And our goal is to show that these two are equivalent. When it comes to the number of learnable parameters, they are equal. Unfortunately, these parameters were initialized in a different way, so we just want to make them equal. All right, so now we take our input tensor and we run it through both of our modules. All right, let us check out the shapes. As you can see, the shapes are identical. And if we compare them element-wise, they also seem to be the same. To summarize, token mixing can be written as a depthwise convolution where the filter is shared across all the channels. So we're back in the implementation and we indeed saw that we can rewrite the token mixing and the channel mixing with convolutions. However, in my opinion, using linear layers and transpositions is way simpler. And honestly, I'm not even sure if I implemented those convolutions correctly. And now it's time to put everything together and write the MLP mixer. Right, the first parameter is the image size, and here we assume that we are dealing with a square image. Patch size will denote the size of our patch. Again, we assume it's a square. Additionally, we also assume that the image size and the patch size is perfectly divisible. These two parameters we've seen before, they represent the hidden dimensions of the multi-layer perceptrons. Hidden dimension will be the dimensionality of the patch embeddings. In the diagram, it represents the number of columns of the table. Number of blocks represents the number of mixer blocks we will have in our architecture. Internally, we will have the following object. The first parameter is the patch embedder, and it will be a conv2d module. And it is one way of taking an input image, splitting it up into small patches, and then embedding these patches. Blocks will be a module list holding mixer block instances. We will have one layer norm that will be applied just before the classifier. And finally, we will have the classifier head, which will be just a simple linear module. First of all, we compute the number of patches. Again, here we're assuming that the image size and the patch size are divisible. And the number of patches is going to stay constant across the forward pass, and it represents the rows inside of the table that you saw in the diagram. So this patch embedder will help us split the image into patches and then embed them. To do this, we are using a 2D convolution with kernel size equal to the patch size and also the stride equal to the patch size. And note that we are hard coding that there will be 3 input channels inside of our tensor. Here we instantiate multiple mixer blocks that will have independent weights. Finally, we create a layer norm and a linear layer that will serve as a classifier. All right, and now the only thing left is to write the forward pass. Right, so the input is nothing else than a batch of images, and the output is going to be a class prediction for each of the samples. So we apply our patch embedding, and it will be a 4-dimensional tensor. One way to think about it is that each pixel in this new tensor represents one patch, and the channel's dimension represents the patch embedding. However, we would like to rearrange this tensor a little bit in order for it to be able to go through the mixer blocks. So here we did 2 things. We collapsed all the patches into a single dimension, and then we just made sure that the channels are the last dimension. Let me show you an alternative way of creating the patch embeddings that is not using any convolutions. All right, we defined a couple of initial parameters. Now we just construct a batch of input images. Let us now take this tensor and rearrange its dimensions. So here we're using INOPS, and we say that the input is nothing else than a mosaic of patches as specified before the arrow, and what comes after the arrow is the desired rearrangement. Note that after this rearrangement we will have a 3-dimensional tensor. First dimensions are the samples, the second dimension represents the tokens, and the third dimension represents the flattened patches together with all the channels. And as you would probably guess, we actually want to take this last dimension and apply a linear mapping to it, and thus performing the embedding. So here we instantiated 2 modules. First of all, we have the linear module, which is supposed to take the last dimension of our rearranged tensor and map it into the hidden dimension. The second module is a 2D convolution, and it corresponds to the patch embedding that was included in the official code. And our goal is to show that these 2 modules are doing the same thing. When it comes to the number of trainable parameters, they are equal. All the trainable parameters lie inside of the weight array and the bias array. The weight array of the linear module and the convolutional module has a different shape. However, the number of elements is equal. These tensors were randomly initialized during instantiation, and our goal would be to make them equal. Let us now run our input tensor through both of these layers and see what we get. Note that we took the output of the convolutional module and we rearranged it such that the channels are the last dimension, and also we collapsed the height and width of the patch image into a single dimension. This single dimension will have a size of number of patches. So when it comes to shapes, they seem to be identical. And if we do an element-wise comparison, it is also the case. All right, so we're back in the implementation. And as you've just seen, it's not necessary to use the 2D convolution to create patch embeddings. We iteratively apply all of our mixer blocks. We then apply one last layer normalization. And then we perform the global average pooling by averaging across the tokens dimension. And then we just run our linear classifier and we are done. All right, so now we would like to verify whether the flags implementation and the torch implementation are equivalent. I guess the correct way to do this would be to compare the trainable parameters or arrays one by one and check whether the inference gives the same output. However, I do not want to spend too much time mapping the flags trainable parameters to the torch trainable parameters. And instead, I'm just going to write a check that compares the number of trainable parameters. It is definitely not bulletproof, and it might totally happen that it is not going to detect possible bugs in my code. However, it's better than nothing. Alright, so we load both the torch and the Flax implementation and name the Flax implementation the official mixer and the torch implementation our mixer. And now the idea is to create a grid of parameters that will be used to construct the modules. And we will just use PyTest's mark parameterize to brute force over multiple different permutations. Alright, let us start with the Flax model. Note that when we construct it, we don't need to provide the image size because it's going to be implied automatically. We generate 2 random keys. And here we just generate a random array. We are going to have 11 samples in our batch, and our images will have 3 channels. This, I believe, should compute the number of parameters of our Flax model. The idea behind this is that we first call the tree_leaves function that is going to give us a list of all parameter arrays. And then we take each of these arrays and we just compute the number of elements by computing the product over all dimensions. Here we run inference and then we store the shape of the output array. Let us now do the same thing for the torch model. Let us count the number of parameters. Let us run one forward pass with a random array, similar to what we did in Flax. One notable difference is that the channels in Torch are always the second dimension. Alright, and now we can finally write the assertions. We want the number of parameters of the Flax module to be exactly equal to the number of parameters of the Torch module. And we also want to make sure that the output shape for both Torch and Flax is equal to the number of samples times the number of classes. All right, so that's the test, and now we just want to run it. All right, so it seems like everything passed. And when it comes to the number of parameters, the implementations seem to be equivalent. Anyway, that's it for today. All the credit goes to the authors of the paper, and I hope I managed to convey some of their ideas without making too many mistakes. Thank you very much for watching the video. If you enjoyed it, don't hesitate to subscribe, and if you have any ideas for improvement or topic suggestions, I would be more than happy to read your comments here on YouTube or on Discord. See you next time.